Hi there, my name is Perrett from the University of Otago School of Physical Education, Sport and Exercise Sciences down in Dunedin, New Zealand. And this is a quick 10-minute presentation on a paper that was accepted to the ISBS conference that was supposed to be held this year, entitled Movement Variability in the Spinal Kinematics of Fast Bowlers. And this was co-written with my supervisors Peter Lamb and Melanie Bussey, also at the University of Otago. So for those of you unfamiliar with fast bowling and cricket, it's a very complex movement. It involves many degrees of freedom moving through a large range of motion. And during this, the body is exerting and experiencing large horizontal and vertical ground reaction forces, which can be over 10 times a bowler's body weight. For this reason, and for a few others, injury rates in fast bowlers are high despite cricket being a non-contact sport. So it's around 1 in 5 elite fast bowlers that become injured every year. And when you look at the location of these injuries, it's the lower back injuries that result in the most amount of time out of the game. Hence the focus on spinal kinematics in this study. Fast bowling can also be very repetitive, so it can be required to be over 300 repetitions of the same movement over a 4 to 5 day period, but we don't know how consistent the movement is over this time. So we don't know the amount of movement variability that is present. There's a good definition there for movement variability, and it's been reported in lots of other activities within and between individuals. So we know that because of the degrees of freedom problem, we can't exactly replicate the same movement from trial to trial. And similarly, each person's going to move in a slightly different way to another person. And it's likely that there's a relationship between movement variability and both performance and injury. But before this can be investigated in fast bowls, we first have to look and see how much movement variability there is. And that was quite simply the aim of this study, to examine variability in the spinal kinematics of a group of sub-elite and elite fast bowlers. And you can see a few photos of what the makeshift cricket net looked like that was set up in the lab. So enough room for a full run-up for each of the bowlers, and they were just bowling into a net which was about 6 or 7 metres in front of the crease. But 11 participants were recruited through the provincial cricket body, which is Otago Cricket, and they were a mixture of first class, provincial A and provincial under-19 bowlers, and each bowler was required to bowl 36 balls as fast as possible without risking injury. They then came back in a week after the first session and repeated the procedure again, meaning that we had 72 balls from each participant. Data was collected through 3D motion tracking using the Vicon system, and you can see an example of what the marker set looked like there that we used. And then the modeling and the calculation of the spinal kinematic variables was done using Visual 3D. And those variables were axial rotational velocity and lateral bending, which were both calculated as movements of the thorax relative to the lumbopelvis. The processing and the analysis was done in MATLAB, so calculation of ball speed from markers that were placed on the finger and the ball, and then time normalizing spinal kinematic variables to the period between front foot contact and ball release, because obviously this time differed slightly from trial to trial and from participant to participant. Variability was calculated using interquartile range just because it best dealt with the positive and negative values that were seen mainly with axial rotational velocity. And then you can see an example of some of the comparisons that were made with the data there. So inter versus intra-individual variability, looking at how the variability changed within and between sessions, and then also looking at a potential relationship between spinal kinematic variability and release speed variability. And what we found is that in general, variability across the group was high. Each individual had their own specific movement pattern, and some were more consistent than others at using this movement pattern. And that can be seen really well in this figure here, which is an angle-angle diagram of lateral bending against axial rotation. The green dots correspond to front foot contact, and the red dots correspond to ball release, and the black and the grey lines represent session 1 and session 2. And you can see that there's numerous differences throughout the group when you compare participants. So for example, if you take the shape that the line follows between front foot contact and release, you can see participant 2 follows sort of a C shape, participant 7 follows more of an L shape. You can also look at the consistency of the movement across both sessions. So participant 1 is quite consistent both within and between the sessions, whereas participant 5 is quite consistent within each session, but quite variable between sessions. And then participant 6 is quite variable both within and between sessions. But the main comparison that we were interested in was between the group variability and the participant variability. And you can see from the numbers there that for both lateral bending and axial rotational velocity, the variability of the group was about 2.5 times higher than the average variability of the participants. And that can be seen in a little bit more detail in these figures here. So in this figure, the dashed lines represent the variability of each participant, and that's calculated as the interquartile range across their 72 trials at each of the 25 time normalized points between front foot contact at 0 and ball release at 100. So effectively 25 calculations of the interquartile range plotted to form a curve, which is what can be seen here by the dashed curves. The average of all 11 of these participant curves gives this black line, which is the average participant variability. And then the group variability is represented by this grey line, which is calculated as the interquartile range across all trials for all participants at each of those 25 time normalized points. You can see that for both variables, group variability is higher than the average participant variability. A couple of other results I'll just present quickly. Firstly, the spinal kinematic variability was consistent within and between sessions. So there are no significant differences at a group level, and any significant individual differences tended to be bidirectional. Release speed itself was consistent, so bowlers weren't getting any slower or any quicker as they progressed from over 1 through to over 6. And there was no significant correlation between spinal kinematic variability and release speed variability. So more variable movements did not necessarily lead to more variable performance in terms of release speed. And that can sort of be seen in this figure here, so no real pattern. But what this figure does show is how much the variability differs within and between session. So the left-hand side of this figure here compares within session between the first 3 overs or early, which is shown by the blue dots, and the second 3 overs or late, which is shown by the red dots. On the right-hand side of this figure, it compares between session 1 in blue and session 2 in red. The length of each line tells us how much each participant differs in terms of their variability within and between sessions, and the direction of the line tells us which variability it is that is differing. So for example, a vertical line like this one here would show us that the spinal kinematic variability has changed quite a lot, but there hasn't been a lot of change in release speed variability. Whereas a more horizontal line like this would tell us that there's been quite a large change in release speed variability, but hardly any change in spinal kinematic variability. So the results that we found, the amount of movement variability that we saw should be considered and also expected when designing future relevant studies. So those that look at fast bowling technique or fast bowling kinematics, even if there are elite level bowlers in the cohort. So they're still going to display both inter and intra individual variability. And because of this, it's important not to generalize the results of a group to all the individuals within that group, because this has the potential to be imprecise. And this sort of highlights the need for individual analyses of fast bowlers, particularly if there's an intervention aspect to a study, because it's not a one-size-fits-all model due to the fact that each bowler does bowl so differently to one another. The final point I just want to quickly discuss is related to the fact that there was no change in release speed as we moved, or as the participants moved from overs 1 to overs 6. And initially I thought that this was due to the fact that fatigue hadn't occurred. But the more we talked about it as a group, the more we realized that, or the more I realized that it's likely that fatigue had occurred. You'd expect this over 36 balls at 100% intensity. But that begs the question, why do we not see any change in release speed? And there's 2 reasons that this could have occurred. The first is that bowlers were not actually trying to bowl as fast as they could, which is a very realistic possibility. But the second, and perhaps the more interesting reason, is that bowlers subconsciously changed their mechanics in order to maintain release speed in the presence of fatigue. And this might help to explain why the magnitude of variability was so high. And if this is the case, then there's 2 potential effects that this could have on the risk of injury. The first is that if the subconscious change in movement pattern is to avoid overloading of the same tissues, then this could be a protective mechanism. But if these new tissues that are now being loaded are not sufficiently prepared, then this could be quite harmful. But the main takeaway from this presentation and from the study as well is that variability is going to be present in fast bowlers. The majority will be inter-individual variability, but there's also going to be some intra-individual variability as well. So we can't replicate the same movements. Potential research directions for this in the future might be looking at how workload and fatigue influence movement variability and result in performance, but this is heavily reliant on being able to measure both workload and fatigue accurately. If this can be done, then you could look at potentially using movement variability as a performance analysis or injury prevention tool, all with the hope of reducing injury risk in fast bowlers. Thank you for listening.